So the topic of today is the mathematical modeling of dementia. And so what this is about, so clearly there was recently an article on the Science News Journal about multi-scale modeling of dementia. So it's interesting to present that as part of these lectures. Why? First, it's related with works that are related to observed phenomena in the brain. It involves several models that we are used to work with. For example, so it's based a lot on the Fisher-KPP equation. You will see in this lecture reaction diffusion and networks. So I think that's a very, very, very interesting topic to present in the framework of those lectures. Of course, this is an introduction. So the idea is to emphasize the main ideas and to work with some simple numerical models that you can implement in live and to grab some idea concretely. Then, of course, this could be a direction of research, of course. But we are going here to be at a basic level, just to present the ideas of those works. And so the outline of the course is directly related to what I just said. So first we'll introduce the biological context. Then we will work on the Fisher-KPP RD equation. We work it on 2D, and of course you can extend it to 3D. And finally, we will discuss a related model of network of ODEs. All right, so this is directly taken from the article that appeared. So the idea is really, it's not to do an original thing, it's just to discuss these ideas that are relevant in neuroscience. So dementia refers to, generally speaking, to some loss of memory, language, or problem solving. For example, people at some point are not able to pay their bills or things like that. And so the most common cause of dementia is the Alzheimer's disease. And so it has been observed that those disorders are caused by, you can see, abnormal brain changes. So there's remarks at the early stages. Sometimes you can see things in brain. Sometimes you can't see it in the measures that you do for patients, but sometimes psychological tests will put evidence on that. All right, and so there's signs of dementia. So problems with short-term memory, maybe. So it's kind of common. So a lot of people in their family have people with dementia, and you can observe short-term memory problem. So people can lose, they don't remember where they put their wallet, have difficulty to pay bills, planning and preparing meals, remembering appointments, and just being lost even in the neighborhood. All right, and so it's caused by damage to brain cells. So this interferes with the ability of brains to communicate with each other. And this affects thinking, behavior, and feelings. This is progressive, and it gradually appears and gets worse. And so, yes, these general things are just, I just took them from Alzheimer, the website Alzheimer.org. Okay, so now so let's get more into the details, and we're now going to looking to have a mathematical view of that. So Alzheimer's disease presents codified stages. And so it has been observed that Alzheimer is associated with the invasion of two key proteins in the brain. What is called amyloid beta. This is the chemical representation of it, of this protein, and tau proteins. Okay. So here you can see, for example, here this represents a healthy microtubule, and you have some stabilizing protein tau. So this is okay, but somehow sometimes they agglomerate in this kind of things, and this is bad. Okay. And so you can track, so scientists believe that you can track the development of Alzheimer's by tracking this, the presence of these things in the brain, of this agglomeration of tau proteins. Okay, and so you can see that when people die, there is evidence of finding those things in brain tissues. So after death. Okay, and so Brack and Brack in 1991 split the disease evolution into 6 stages, and they start here in what is called the entorhinal cortex, which is somewhere here. Then it goes through hippocampal region, which is known also as limbic system, some part of the limbic system, and then it goes to the temporal lobe, and then occipital lobe. So you can check that on the internet. Those are different regions of the brain, and then it goes to the whole neocortex, and the lesions worsen with time. Okay, so here this is taken from different sources. You can have a look at it if you want. All right, so now what are we going to do today? So first, we're dealing with the, so this is the Fisher KPP equation. So in other courses this year, we already considered this equation, but it was here just the Laplacian. And in fact, in 1D, so it was the second derivative with respect to the variable space. Now you can do it in more general way, and you can choose your space to be some bounded region in R2 or R3 or Rn. And instead of the Laplacian, you consider this this term, which is more general. Okay, so by doing this, so this is taken from the article in Gorelli, and here they simulated this equation with some D, and so these are the finite element methods. So it requires to work with some software that can do that. And then they were able to represent the evolution of the disease. All right. So today, what I propose is an interactive work with you. And the idea is just to work on the two-dimensional reaction diffusion of type 1, so the Fisher KPP, and to see how we can use the anisotropy, meaning that the coefficients will not be the same in D, to generate some preferred directions in the propagation of here the disease, or here the concentration of the tau protein. So here in their model, the U, which they call C, actually refers to the concentration of the tau protein in the brain. Okay, so all right, so let's do some exercise. So first, just to be able to deal with that, just do the details. So if U is a function from Rn to R, develop this term just to that you know exactly what you are doing. Then there's a classical method, for example, the finite difference method. You can discretize the second derivative of the Laplacian. So here, how would you discretize this term, and then implement it with relevant choice of D and with your favorite software. So that's the program that we are going to deal with now. All right, so let's do that. Let's do these details. So first, what's the gradient of U? So the gradient of U is just this vector. So you just take the partial derivatives of U, right? Now let's D be the matrix D11, D1N, and here DAG. All right, so I need to compute. So now D applied to the gradient of U will be a vector, and here I will go sum the J from 1 to N to G1J, and here, So here, Okay, you just apply the matrix D to your vector, and so the general term will be sum to J from 1 to n of Dij du dxj. And so as a consequence, now if I take the divergence of this, by definition of the divergence is just the sum from I to n of the partial derivative with respect to xi of here the component. So it will be sum from j 1n dij du dxj. All right, but so I assume D to be constant, right? The matrix is constant, so I can just do that. So it will be sum from ij from 1 to n of dij, the second derivative of u with respect to xi, xj, right? So that's my term. So finally, we get that gradient, the divergence of the D gradient U is, when D is a constant matrix, is sum from I, J, going from 1 to n of Dij, the second derivative of U, and the partial xa xj. All right, now what I ask you to think about is the following. So you know that if I want so let's assume that I have only one variable. So assume that we work on R. You know that I can write, so U of x plus h equals U of x plus U prime x h plus U second x h2 divided by 2 plus some O of h2. And if I do it at minus h, I will get U of x minus U prime x h plus U second x h squared divided by 2 plus O h squared. So if I sum up the two, I obtain that ux plus h plus ux minus h minus 2u of x equals u second x h square plus O of h square. So finally, divided by h square, I obtain that uxx equals ux plus h plus ux minus h minus 2ux divided by h2 plus, so it's not now an O, it's an O of 1 or epsilon of h, and epsilon of h is a function that converges to 0 when h goes to 0. So yeah, so it's classical then to implement to discretize our domain in 1D by taking this approximation. And you forgot just that. All right, so can you propose something analogous for, let's say I work with 2, if I want to, now if I want this term here, let's say n equals 2, and G is symmetric, right? Assume that G is symmetric, or not actually. G doesn't need to be symmetric, but yeah, can you propose something doing the same as here, but to discretize this whole thing, right? Can you come up with, can you do the same thing, but for all the terms here? So the question is, so let's say now n equals 2. Can you provide something by secant u x square or okay, so this is the exercise that I propose. Do the same thing from these terms. So actually this one will be the same, but this one, you have to compute actually this one. Okay, so hopefully you could do the computations. So I'm not giving all the computations here. What I'm going to do, however, is to focus on the case that we are going to implement right now, which is the case when our matrix D here will be, for example, so A, 0, 0, and D. And so we'll consider two cases, either A equals D and A different of D. So, so from the numerical implementation, so this will give us that. So we'll consider A ux x plus G u y y. And so this will be approximated by A u x plus h y plus u x minus h y divided by h 2 plus b minus 2, of course, u x y plus b u x y plus h plus u x y minus h minus 2 u x y divided by h2. Right? Okay, and so what I propose to do now is to share with you details of a program and to look at what we obtain when we simulate a simple Fisher KPP equation on a square. So let's do that. Yeah. So here is the program that is intended to simulate our equation. So you can see here So these are, so A equals 2 and D equals 1. So these are the coefficients of my matrix here. I'm not going to use B. Here, so here is the implementation of the Laplacian. You can see here, it's with D is the identity here, but my Laplacian 2 here has here the D and A that appear, all right? And so how it's computed, so it uses the property of the matrices because, so it's a Python program, because the library matplotlib will be able to do this fast with the matrices. So this thing, you just work with the matrices, and this is exactly our, refers to the computation that you did as an exercise. This you can forget about it. And so here it's it's intended to show the two-dimensional patterns. What did I do? So 100, it's the number of the points in the discretization in the 2D grid. This is my time. This is my time step, and so this comes from it's simple. So it's yeah. So what we choose here is our, yeah. So our space is 1. Okay, time step space is 1, and time space is 001, 0.001. All right, and then here is the program that will compute the solution. And here is my partial differential equation. So you can see here appear the term from Fisher KPP, right? And then, so let's try that. So I will implement here Laplacian U, and okay. And let's look at the program. So I run it, and let's see what I obtain. All right, so you can see that after T equals 50, I get that. So what's the initial condition? It's important. So first there is that and that, but what I want to show you also is this one. So what is my initial condition? So in yellow, it's something that is close to 1. And in black, it's 0. So I start with an initial condition is a little spot here that with value 1 in this spot. And you can see that thanks to the diffusive property, the 1, and with the Fisher KPP equation, the 1 progresses. So this is the idea in the article, that is the concentration of the tau protein will progress to the whole brain. So here is just a simple mathematical representation in 2D, but that's the thing. Now, if I want to give some preferential direction to the front propagation, I can just change and choose here, instead of working with the Laplacian, I will work with Laplacian 2. And So, all right, and I will put a stronger coefficient here. So my A appears here. But there is a, oh, so no, top has to be here, left and right. Yeah. All right, then I will run. So I changed here. As you can see now, my A and D have different values. So I put a stronger value here. And this is actually, this is the vertical direction. So I put a stronger strength in the vertical direction. And now let's see what we obtain. So, yeah. So, yeah, so by putting more strength in the vertical direction, actually, because in the diffusion, the front here propagates like that. No, no. So sorry about it. No, this is the horizontal direction, and so that's square on. So here, sorry, it's left, so everything's good. Left here represents the sum of the left terms for the in the differential terms, and it appears here. Okay, so I put more strength in the horizontal direction, and you can see that the front propagates more here in the horizontal direction in comparison with the previous one. So to make it more even effective, let's try one other thing. Let's put 4. Hopefully it works, and let's look at that. All right. Okay, so you can see, so by playing with these coefficients, we can also put that here. We are able to induce a preferred direction in the diffusive process. All right. So this is clear here. The front propagated in the horizontal direction, but not in the vertical one. Okay. So this program will be available to you, and you can play with it. All right, so next. So instead of considering a PDE, you can also consider a network of ODEs. So at each site, you consider some value of the concentration at some point in the brain. And so this point is referred to the index I. So you have several ones, and then you will compute the concentration of the protein with this equation too, right? And for example, you can say that the LIG can be proportional, or so the more you are far away between two cells, and the weaker is the coefficient here. So that's, so for example, they did that in here. Again, this comes from this paper in the Science News. When you have a bunch of UI here, and you see that so when you are blue means that the concentration of tau has reached a point. The bluer and the higher in concentration of tau. Okay, so let's try to do that again in a simplified version of it. So, all right, next we are simulating our network. So you see, I'm just using the solver from Python. So my ODE is the important function. So if I go to my ODE, so here is the matrix. That corresponds to the sum with the row. And then here you have the nonlinear term appearing in the Fisher KPP equation, all right? So the matrix is here. So basically, each node is connected with actually six in general, 6 neighbors. That is, for example, if the neuron I is connected with the neuron I+1 with strength of 1, it is connected with the neuron I+2 with strength 0.5, and with the neuron I+3 with strength 0.1. Okay, so here this appears here and here, and also here. Okay, and it's symmetrically connected with the neuron I-1, I-2, and I-3. You can see that here. All right, and okay, and these are diffusive type because you see that the sum here minus or 3.2 is exactly the sum of 0.1 plus 0.6 plus 1 and times 2 gives you 3.2. All right. And this is a diffusive type. Now, okay, I'm going to run. So again, what is everything? My initial condition is 0. Everything start at 0, anything but the first term here, so which starts at 1. Okay. And those are the value of alpha and rho. So you have a stronger effect on the reaction term, if you want, and the diffusive term is 10 times smaller as the reactive term. Okay, let's run it. All right, so you can see that. So my U1 start at 1, then my U2 will go to 1, 2, the same for U3, and the same for U4. So actually, this is linked with the ODE because 1 is a stable, attractive point, while 0 is repulsive. So they start at 0, but because of the diffusive terms, they are kicked out, and after they reach 1. Okay. What we can do is also we can do a movie. So it's here. I prepared already for you just to be closer from the original application. So this is Python stuff, but you can write a movie. So now I will do as in the picture. Each node will be represented in the space, and the blue represents the strength of the concentration. So if something is white, there's no protein tau, but if it becomes blue, it means that there is more protein tau. And so I prepared for you a movie. So let's find it here. I will first try it, and then I will share it with you. So okay, so let's do that. All right, so here's the movie. So as you will see that, so this is the initial condition. So you have 10 nodes, okay? And so each node is in the diagonal. So at 0, 0, you have one node, or then at 1, 1, you have another one, at 2, 2, another one. So you see only one blue disk because the other are at 0. So the other are right. Now I will run the movie, and we will see what happens. Okay. So you can see that the tau propagates like that. All right. So as I told you, the network topology is that the first node is connected with the second node here with a strength 1, this one with a strength 0.5, and with this one with a strength 0.01, 0.1. And the same for all. The initial condition is start at 0, and it's the two ways. The coupling is symmetrical, and it's a diffusive coupling. So let's run it again. All right. So that's basically the, oh, sorry. So that's uh, that's all for today, and hopefully I can see you for the next lecture.